Okay, let's get started, everybody. So today, this is week 3 of our 7-part series on essentials of math modeling for the M3 challenge. Today, we're going to be tackling data analysis in MATLAB and Excel. Before we get into that, I just wanted a couple of announcements and reminders. I just wanted to remind everybody that the M3 challenge is quickly approaching. The challenge weekend is exactly a month from now, and February 25th to 28th is the weekend of the challenge. And registration closes a little bit before that, February 18th at 4 p.m. Eastern time. So if you are interested in competing, start thinking about building a team and thinking about who can be your advisor and getting registered and all that. Another thing, I just wanted to thank everybody for their participation during our workshops. These last 2 sessions have certainly been really helpful for us and hopefully very engaging to all of you. And we would like to hope that, or like to ask that you continue to participate so that we continue to make this workshop series a success. The third thing are that these workshops are being recorded and uploaded to YouTube, usually within a day after every single session. So if you are interested in looking at these workshop sessions after the fact, or if you are unable to come to a specific workshop and wanted to catch up, you're more than able to do that. If you take a look at our chat, one of our lovely volunteers has put a link to all of our relevant information. The last of those links is for the YouTube, the playlist, where you can find all of our videos. All right. And also before we really jump in, I wanted to just remind everybody how the session is going to work. So in the first hour, I will be tackling the data analysis portion. I'll be showing you a little bit of Excel and MATLAB in order to work with data, read in data, and plot some data. The second hour, Wesley is going to take over and will be taking us through the 2017 M3 challenge problem. And like in our very first workshop session, we'll be taking a look at the problem and thinking about how to build a framework for a mathematical model. Okay. We also have most of our volunteers here. These are our lineup of lovely people who are here to help us answer any questions that you have. So if you do have any questions that you'd like answered, please use the Q&A feature of Zoom, and one of our volunteers will be able to answer your questions as the workshop is going on. If I've asked a question and I'm posing it all to you to kind of answer, you can use the chat feature to communicate those answers to me. Also, if you have any questions about the competition in general, or maybe some tips and things like that, myself and Owen have competed in these competitions beforehand, and we'd be more than happy to try and share any guidance that we might be able to. With that, let's actually get started with our workshop series for today. The first thing we're going to do is talk a little bit about spreadsheet applications like Excel or Google Sheets. These options, Google Sheets and Excel, are really, really nice at getting quick and easy viewings of your data sets that you might be getting from competition or anything like that. These should usually be your first step in the kind of competition setting, to open up your spreadsheet in Google Sheets or Excel to see what it looks like, to see what kind of statistics or summaries have already been given to you, any definitions of certain variables, things like that. This is a really nice, quick, and easy tool to use. And also, you may find out by opening up your data set that you might need to clean your data set in order for you to actually be able to use it. And as an example, we're going to take a look at a data set that we've already looked at. Let's see, it's this one right here. So you may remember I have shown you this data set way back when, 2 weeks ago, 3 weeks ago, during our very first workshop session. This is the percentage of high school students who've used e-cigarettes in the last 30 days by gender, race, ethnicity, and this was done by the National Youth Tobacco Survey. Over the course of these 5 years, this shows the percentage of teens who have used e-cigarettes in the last 30 days. This is the overall number, and then they've also broken it down by gender and ethnicity, right? Some interesting things to note about this data set, right, is that in certain cells, like this cell, all of these cells, there are multiple pieces of information in each of these cells, right? And this makes it hard for applications like Excel to really render what's going on. So I actually did this example here for myself. But if I wanted to try and add this element and this element together, I would get an error by Excel because Excel doesn't know how to deal with these parentheses and this dash in between the numbers, right? Excel doesn't know that this is just a series of 3 numbers that I'd like to have added together or multiplied or anything like that, right? It doesn't know what to do with it. So we can already see that we might actually need to do a little bit of data cleaning in order to get started with doing some statistical analysis, right? If you're a whiz at stuff like regular expressions or data string formatting in programming languages, you might be able to do stuff like that in those kinds of settings. However, these spreadsheets are really nice ways of visualizing yourself cleaning up data. So this is always a really nice way of doing that. I've kind of cleaned up the data set by rewriting it over here. So on this column, I've plotted, or I've put down the year, and here I've put down the overall data. So I've taken the average value from each of these cells right here. And then I've plotted them on these 2 plots, right? These are the same plots that I've shown in week 1 of the session. So if you look back at the PowerPoint presentations, you'll find these same two slides or these same 2 figures. What I've done on this figure is I've created a linear fit, which you can do fairly easily in Excel. And then I've also plotted this Gaussian fit, which I took from one of the winning solutions from this year, 2019 problem. I've also generated the values from an SI model, and we're going to talk a lot about SI models today, and we'll talk a lot about SI models next week when Julie takes over. And you can see that I've been able to plot the percentage of team vapors versus time as a scatter plot for the data sets that we do have. And I've also been able to kind of make predictions as to what the future trends should be in teen vaping over time, right? So using Excel, we already have a lot of tools available to us, but there are certain limitations in certain ways where programming languages can make our lives a lot easier in certain ways. So we're going to be spending most of our time today in MATLAB, working with data and doing a lot of visualizations there, all right? So let's come back over here. So last week, Owen took us through the MATLAB programming language, and he took us through a lot of the basics of how to work with MATLAB and some basic programming things in general. So we covered stuff like arithmetic, lists, logical operators like Booleans, and for and while loops, right? For today, to kind of remind ourselves of a little bit of how to use MATLAB online and to get our feet wet a little bit, I'm going to be doing some experiments with lists. I'm going to be doing a couple of additional kinds of commands and programs that you can do with lists to kind of motivate some of the stuff we'll be doing later. So this is the code that should be published now on my File Exchange website. So if you want to download this code for your future reference, you can do that. What I'm going to do is I'm going to start here in this section with list properties. And I've started by defining 2 very maybe boring or not unique, not creative at all list names, first list and second list. And I've populated them with 5 elements each. And I just uncreatively took elements or took values from the Fibonacci series. The first thing I'm going to do is I'm going to do what's called a concatenation. I'm going to combine these 2 lists together. The first thing I'm going to do is combine them horizontally. I'm going to comment this line out so that we can just see what happens here. And then I'm going to run my section. Okay. So what's happened here? Oh no. Let some cats out of the bag over here. Let me comment out. Excuse me. So over here, you can see this is the line, and here is the result on the right-hand side. Right? So you can see what I've done is I've just appended these 2 lists together horizontally. So now I've created an array of 10 elements here, which contains all the first 5 elements of the Fibonacci series. Right? What I can also do is vertically concatenate these lists. And I can do that by simply changing this comma to a semicolon. So when I run this section, again, I get the horizontal concatenation from here, and I also get this vertical concatenation. So now I have an array of two lists that have just been put one on top of the other, right? As another example, and just more of a cautionary tale, I've created yet another list with another two elements from the Fibonacci series. And let's do a little bit more concatenation. The first thing I'm going to do is horizontally concatenate. We're in that section. And you can see, just like before, I took first list and yet another list, and I just combined them. All right. The next thing I'm going to do is vertically concatenate. And turns out I actually got an error. Error using vertcat, which is just a shorthand for vertical concatenation. Dimensions of arrays being concatenated are not consistent. So this is my first question to you all. Can you try and parse out what this error message is telling me? What is it that I've done wrong in this line of code? I'll give you all like a minute or so. Give you all another 10, 15 seconds just to make sure. Yep, okay, great. Yes, so exactly what I've seen from some of these chat responses. The number of elements are not consistent with each other. So in this case right here, I had 5 elements in each row, and they were able to go one right on top of the other in a one-to-one correspondence. Here, because I only have 2 elements, MATLAB doesn't know where to put 89 and 144 in relation to these 5 elements, right? So one thing I can do to fix this problem is, because I don't know the next numbers of the Fibonacci series off the top of my head, I can just add a whole bunch of zeros, and here we go. I actually was able to fix my error by just adding in any number of elements that I needed, right? And you can see that both the horizontal concatenation and the vertical concatenation added these extra zeros. So if this is something that you would not like, you have to find a different way of concatenating them or filling in this empty set, right? Okay, great. I'm going to comment this out so that I don't get an error. Another thing that you can do with lists that'll be important later on is that you can index lists using Booleans, right? So this is a little confusing, so I'm going to just take this one line at a time. The very first thing I'm going to do is I'm going to check whether or not the values of first list are even or odd, or I'm going to output true if the element is false, or if the element is odd, and output false if the element is even, right? So mod, if you'll remember, gives you the remainder when you divide each of the elements of first list by the number 2. And for an odd number, this should be 1. So this value, if I run this section, this list should give me this array right here, where, remember from last week, 1s correspond to true and 0s correspond to falses. And if you compare first list to our logical array, you can see that the first 2 elements are clearly odd and the last 2 elements are clearly odd, but the middle element is not, right? So now what happens if we apply this variable here, this list is odd, to first list? Now I actually get a shorter list where I've ignored that middle entry because it was not odd, right? I've only recovered the odd numbers from here. All right. So this can be a little bit tricky to think about, and it becomes, you have like a list nested within another list. So I do highly encourage you to play around with this code and experiment for this stuff yourself. The big takeaway from last week that I will kind of remind you about this week is that the best way to learn about programming is by doing yourself. So take advantage of the code that we have published online. Try and mess around with it. Make an error on purpose and try and fix it. Find different ways of fixing it. If you really cannot, fix your mistake, you can always download the code again, right? But making mistakes and figuring out how to fix them is certainly one of the hallmarks of programming. Certainly something that you have to do plenty of times when you're actually programming in the wild, right? So with that, let's move on. One of the big things we're going to do today is actually implement one of our first mathematical models a little bit more formally. We're going to talk about SI models, all right? So SI models are a model for disease spread in a given population. We're going to talk a little bit more about this next week, again, with difference in differential equations, but I've applied the most simple kind of SI model imaginable. So suppose the value S represents the fraction of susceptible people in a population, and suppose the value I represents the fraction of infected individuals in a population, right? And so what we're thinking about is we have a group of people, some people have some disease, and they're able to infect susceptible people by interacting with them. Our interaction term is given by this portion right here. So mathematically, we can kind of think about the number of times an interaction occurs between an infected person and a susceptible person, and then multiply that by some constant, which is called the infection rate, right? So if we want to know what the number of susceptible people is, or the fraction of susceptible people is at a certain time t, what we do is we take the susceptible population at the previous time, let's say the previous day, and we subtract off the number of people who became infected over the course of that day, right? And then equivalently, the number of infected people would be the number of infected people from the day before, added to that, the number of people who became infected with the virus or the disease or anything like that, right? So I have another question for you all, something that's a little bit more challenging. I'd like to ask you all, what assumptions are we making about our population of people or about the disease itself that kind of lead us to this set of equations? So things I want you to think about are population size, the nature of the disease, things like that. What kinds of assumptions are we making when we've written down this equation? All right, yeah, good. I'm getting some good answers. I'll give you all another, let's say, 20 seconds. Okay, great. Yeah, so I've got a couple of good answers. First off, the total population is constant. So there's no birth, there's no death. There's no death because of this disease or just naturally, anything like that. Everybody's equally susceptible. So if there are only two types of people in our model, those who can get the virus or the disease and those who have the disease, right? People can't be infected twice, so people are not able to recover, right? Let's see. Yeah, I think. We're also assuming that the disease does not increase or decrease its power to spread. The only way that this disease can spread is if there are more infected people, right? Great, awesome. Thank you very much, everybody. So now what we're gonna do is implement this model in MATLAB, but we're gonna come back to this assumptions, these things that you all have thought about towards the end of our presentation. So let's implement this. So I'm going to just briefly walk through this code, what it does. But again, I encourage you to kind of mess around with it yourselves. The very first thing I'm going to do in this kind of section of code is just initialize or start up our model. So I'm interested in the spread of a certain disease over the course of 100 days. And I'm going to initialize two empty arrays. This is going to contain all of the data that we're going to collect from our simulations. So S is going to be an array that contains the number of susceptible or the fraction of susceptible people at each of our days, right? And I have an array of days plus 1 because I'm thinking of starting at day 0 all the way up to day 100. So that's 101 days. And then equivalently for the number or the fraction of infected people. The next thing we need are our initial conditions. We need to know what the starting point is. We need to feed in a starting point to our model in order to figure out what's going to happen in the future. So I'm going to assume that 99.9% of our population is susceptible to a disease and 0.1% of our population has a certain disease. And A, again, this is a model parameter or an independent variable that we might need to tweak as we go along or figure out from literature or do some statistical analysis to find out. But this is our infection rate. All right. The next thing I'm going to do is actually perform our simulations. I'm going to move forward in time. So this for loop is going to count the number of days from 1 to 100. And at each day, I'm going to calculate the number of new infections, right? This is just based off of the equations that I had written down in our slides. And then from that, we know how many new infections there are in a given day. So I'm going to subtract that from the previous number of susceptible people and add it to the number of infected people, right? And that's how I get the new values for susceptible and infected people, okay? That's all there is to it. I'm just going to run this section and our code ran perfectly fine. But now we actually have to take a look at what our simulation did, right? So let's display our results for S, the fraction of susceptible people. I'm going to hit run section. All right. And so now over here, we can see what the value of S is at each of these indices, right? So we start right here with our initial conditions, just like we had initialized. As we start, we see that there's not a big change in the number of susceptible people. The fraction stays pretty much close to 1. Then all of a sudden, we start to dip into the 80s. Pretty quickly, we go into the 70s, the 60s, 50s. All of a sudden, we're all the way down at the 20s. And then we're at a pretty small number by the time we hit day number 100, right? So this is cool. We can kind of just see from this list that the number of susceptible people is decreasing, right? The next thing I want to do is display this value S plus I. So let me hear your guesses as to what you think the output of this would be. If I add the number of susceptible people and infected people, this goes back to one of the assumptions that we're actually making. Yep. This is great. Give people maybe another second or two. Yep, awesome. Okay, yeah, so the number should always equal 1. For every single value, let's make sure of that. And lo and behold, the sum of the number of susceptible people and infected people is 1, right? This was an assumption that we made mathematically, right? That the total population is constant. So whatever value, whatever our original sum should be between the number of susceptible people and infected people, it very much should be exactly the same value, right? This is a way to check to make sure that your code is correct, right? If you're seeing your model is, adding people or subtracting people when you're not supposed to be, then that probably means that you have some kind of bug in your code, right? So this is always a good sanity check to make sure that your code is actually doing what you want it to do. Okay, so great. We have our first simulation. We have some data involved. However, it's really not tractable to just show a big list of data points on a report, right? So this is where we get now into plotting. And MATLAB has a ton of really awesome plotting features that you can use to make really, really nice plots. So some of the ways in which you can plot data would be to create a scatter plot. So if you include the x coordinates and y coordinates of a bunch of points, it'll plot a whole bunch of points in a plane. You can also create a plot which implies a line plot between all of these coordinates. So you're just creating a straight line between a set of these x coordinates and y coordinates. You can also create a histogram. So if you give some frequency kind of data, or it'll plot frequency information based off of your data for a given number of bins. So now let's go back to our SI model and actually use some of these plotting features, right? So the first thing I'm going to do is tell MATLAB I'm going to initialize figure and index it by 1. And then I'm going to plot the number of infected people over the course of my simulation. Okay, so I have 101 days in my simulation. So this would be our x-axis, and our y-axis is the fraction of infected people. Let's run this section. And so now you can actually see visually this kind of nonlinear behavior in the number of infected people. So initially, there are not a whole lot of infected people. It takes a little bit of time for it to ramp up. After a while, it really ramps up because there are a lot of infected people. There are a lot more interactions between susceptible people and infected people. And then after a while, pretty much everybody becomes part of the infected group. There's not a whole lot of people to turn into the infected group. So it kind of levels off. This is what's called a logistic curve. All right. So now what I want to do is I would like to also plot the number or the fraction of susceptible people on the same plot. So I'm going to uncomment this line of code and run section. And it turns out that MATLAB actually just created a new plot for me. It didn't put them both on the same figure. And it turns out that plot will erase previous curves unless you explicitly tell MATLAB, hey, I want to add extra stuff to this figure. So in fact, here's the correct way of putting both of these curves on the same figure. I'm going to plot the number or the fraction of infected people. I'm going to tell MATLAB, hey, hold on. I'm going to add more stuff to this figure. Then I'm going to plot the fraction of susceptible people. And then finally tell MATLAB, hold off, I'm done. So let's run this. And here we go. So now this blue curve is supposed to represent the fraction of infected people. And this orangish curve is supposed to represent the fraction of infected. Oh, excuse me. I think I mixed up my words there. This is infected people. This is susceptible people, right? So you can tell that by about around day 70, day 75-ish or so, it looks like the number of people in both infected and susceptible categories are about the same, right? So now we can actually visualize what's going on in our simulations. That's really cool. And then you can also, if you're feeling pretty proud of your work, you can save the plot, right? So using the save as function, you can save this plot, and I am going to save it as my first figure.png. And there we go. So now we actually have it so that we can actually apply it and put it into our report or our presentation or anything like that. Okay. Now this is kind of the part where I kind of preach to you all a little bit. If you were to put this in a report, let's say for your M3 challenge paper, or if you were presenting this to city planners, they would take a look at this image and say, wow, cool colored curves. What the heck is this saying, right? There's no extra information from this figure. So without this extra information, it's really hard to know what it is we're actually doing here, right? And this is something just that I'd like to note about readability. the readability of your plot really, really matters. Being able to have a plot that it can stand out on itself and give people good information is really important. So what I'd like to ask you all is, what kind of elements to our plot should we add so that we can make it easier to read? What kinds of things would you like me to improve on this figure so that you can give this to somebody else and they can understand what it is we've just done? Yep. Yeah, awesome. These are great recommendations. So yeah, some of the things I thought of, we should add axes labels, we should add units, a legend, some titles, to things, some words basically that will allow others to understand your awesome results, right? And you can, actually, let me come back over here. Some examples, some of the functions that you can use to actually apply some of these things are called X label and Y label for the axes titles. Legend will create a legend somewhere on your figure with these specified sets of titles for each of your curves. Oops. And then you can also do things like add a title and things like that. Again, I would encourage you to look up the MATLAB documentation because there's way more than I can fit on any one slide as to all the cool things you can do. But this is kind of what I would like to do to make my plot really nice and readable. So what I've done, I haven't done anything differently in terms of the information, right? I'm still plotting the number of infected people over the course of these days and the number of susceptible people over these days, right? But I've added a tag or label on my curve so that it can be shown up in my legend. And I've also done stuff like I've changed the font size. I also prefer the LaTeX font over this generic font. I think it looks a little bit cleaner. I've added X labels, Y labels with kind of the implication of units in these titles, and I've given a title, right? So now from here, and I've also made these curves a little bit thicker so that you can see them a little bit easier. This is more of a stylistic choice. But now, if you were to give people this figure without anything else, maybe if you added a caption, people would get the gist of what you're predicting would be a disease spread model, right? So this is something that I think is something that should be thought about a lot when you're making figures and stuff. This is really something fairly easy that you can do, but makes a big impact on judges or report writer or report readers or anybody like that. As another quick example, before we move on to our next topic, you can also create a similar plot using scatter. So what I've done here is I've changed plot to scatter, and I've also only plotted the first 20 days of my infection, right? Because here now you can see that you get a different idea of what's going to happen over the next, let's say, 3 weeks of this disease spread. You can see that not a whole lot is going to happen, right? So this might be some indication that we have a little bit of a buffer before the big wave hits us, so that maybe we can make some public health measures or something like that about this, right? One thing to note is that if you're plotting something on the x-axis for days, it seems to make a lot more sense to people in terms of readability to make this a line plot. So while you can make a scatter plot of this data, it seems to people, and or at least to me, that a line plot makes a little bit more sense because time kind of rolls continuously, right? But this is getting into more stylistic choices and stuff like that that you might be able to have your own liberties with. Okay. Does anybody have any questions before I continue on? Again, if anybody has any questions, feel free to use the Q&A section of Zoom so that you can get your answers answered by one of our volunteers. Okay, great. So I'm going to shift gears a little bit and now talk about random numbers. So MATLAB has some built-in functions for pseudo-random number generators. Some examples of these functions are rand. So if you use the function rand with a number n, you get out n random numbers chosen uniformly between 0 and 1. If you use rand n, you get a normal distribution. So you get n normally distributed random numbers. And to kind of give you a little bit of some examples on these random numbers, we're going to do a couple of illustrations with plots. So we're going to sample 2 uniform distributions and then plot them on an XY plane. And then we're going to sample points from a normal distribution and plot a histogram. All right. So this will also give you a little bit of an understanding of how these other kinds of plot functions work. Okay. So this is the section for creating 2 uniform random numbers or sets of random numbers. The first thing I'm going to do is generate 5 random numbers 2 times. So the first time I'm going to create my X values for my plot. The second time I'm going to generate my Y values for the plot. And then I'm going to plot them in a scatter plot. So let's run this. And you can see that I got 5 points that, seemingly randomly were distributed throughout this area, right? And turns out that if I keep clicking run section, you'll notice that each of these points will change locations. So click run section, different orientation, different points, run section, run section, run section. Every single time I get a new set of points, right? And it's random in a colloquial sense, right? It just doesn't seem like something that you can predict, but is it truly a uniform random distribution? One way to kind of see whether or not this is true is by increasing the value of n. Well, let's just do 500. I don't want MATLAB Online to be mad at me with Zoom running. And you can see now you have more even spread of points throughout the span of 0, 1, and 0, 1, right? So indeed, this function does give out a uniform distribution, okay, or something that's pseudo-randomly normally distributed, okay? So the next example is going to come from a normal distribution. So I'm going to take 5 normally randomly distributed numbers and then plot them on a histogram. So this histogram tells me the frequency of times that I get a number in this kind of range from Y, right? So from just 5 samples, you can clearly see that this does not look anything like a normal distribution. A normal distribution has that kind of characteristic bell-shaped curve. One thing that we can do to improve this is by, again, increasing our number of samples. And now we have something that looks a little bit more like a bell curve, right? But these boxes are quite wide. So one thing we can do to make the boxes a little bit thinner and hopefully match the shape a little bit better is increase the number of bins. So there are 10 bins here in this area. Now we're going to have 50. And you can see that the bins did decrease in size, but you also added a lot more noise. So while you can maybe make out the shape of a Gaussian curve a little bit better, you still have this extra noise. So let's add some more numbers. And you can see that the noise kind of decreased a little bit, and you can see a little bit more of that characteristic shape, right? And again, we can see that we do get something that looks, at least to our eyes, like a normal distribution. Okay. Any questions on random numbers, things like that? We're going to be practicing with with random numbers a little bit more, I guess, in 2 weeks when Xiao takes us through some probabilistic models. Okay, awesome. So for the last, let's say 20 minutes, a little bit less than 20 minutes of our time, we're going to now talk a little bit about data importing and data manipulation in MATLAB. So MATLAB has another built-in data structure called a table that's really good for working with really large, complex data sets, right? Some of the commands that we'll be using are reading tables from CSV files. So this read table function takes in a CSV file and saves it as a table, and I'm calling it df here. You can preview the first couple rows so that you can kind of just see what the data frame looks like or what the table looks like without it just completely populating your entire screen. You can isolate columns from your table just by doing dot the name of your column. You can also convert your tables to arrays like lists so that we can do some of the commands that we've seen before with the caveat that you have either an array or a table of numbers only, or a table of, I guess, strings with the same size. I think that might work. So now what we're going to do is we're going to take in coronavirus data from the United States, and then we're going to plot cumulative case numbers for certain counties. All right. First thing we're going to have to do is import this data. So if you go to our Google Drive, which you might be able to find if you scroll up in our chat, we have a link to our Google Drive where you can see our presentations as well as any of our data sets. So it looks like, oops, over here. So these are all of the slides from previous sessions. And this Excel sheet is a data set that I got for COVID confirmed cases. Okay. And I'm going to just move over here to Excel so that you can at least see what we're dealing with. So it starts off with just information on county level data. So you can see that each county is given its own unique code, the name of the county, the state in which the county is, and each state is also given its own unique code. And then starting with January 22nd, 2020, this gives you the cumulative number of cases in that county over time, right? So if we just take a look at this county right here and move over to the right, eventually we'll find that on March 24th, 2020, this county reported its first coronavirus case. The next day, it reported 3 more cases, so a cumulative total of 4. Then 2 more cases, couple days of no cases, right? And then it just kind of keeps increasing and increasing. We know the story, right? So this clearly is an enormous data set. We'll kind of get a sense for that in a little bit. And it's pretty hard to kind of work in Microsoft Excel or Google Sheets with a data set this big, which is why tables in MATLAB really come in handy. So the first thing I'm going to do is use this read table function. So I'm going to read in a CSV version of that data set. And I've also added these extra conditions so that this table can remember the columns, remember each of these column names. Okay. And then the next thing I'm going to do is use this preview function so that we can see what the data, what the table looks like. One section. So now we get the first 8 rows and we have all of our columns organized as we expect. And we can see, I can keep on scrolling. There's a lot of data here, right? There's quite a bit of stuff. Now to kind of figure out how to use tables, one thing we can do is we can ask for all the county names in the United States. So let's run this. Oops, I'm gonna comment that out. And you can see every single county in the United States with a couple of extra ones because there's, you'll notice that there's also statewide unallocated for every single state. I guess if there was a case where they couldn't assign it to a specific county, they just added it here. All right. You can also index your table similarly to how we indexed lists. And what I'm going to do is index by the name of counties. So let's say that I was interested in the COVID data for Uinta County, Utah. All right. And what I'm going to do here is I'm going to ask for a string in the county names that matches this string right here. And then I'm going to display it and run section. Let's not display all the, well, I guess it doesn't matter, but let's not display those counties. So this is the result for this section. And it turns out we actually got 2 results back. Can anybody give me some suggestions as to why this happened? Why did I get 2 different counties out? And maybe what can I do to fix this? Give people maybe another second or so. Yep, okay. Good, I got a couple of suggestions. So one thing I could do to fix this issue is add an H here. Run section. Turns out that I got now the county that I was interested in. So the reason this failed the first time is because all I'm asking for is, does this sequence of letters UINTA appear anywhere in the county name? And turns out it appears twice in this data set because the data set's so big, sometimes you don't really consider these kinds of occurrences, right? So one thing you can do is change this to Uinta, and then maybe even for good measure, you can say county, right? That'll certainly fix the issue. Let's say I spelled county wrong. Nope, right here. Another thing you could do, I'm gonna comment this one out, is I can also, I think somebody else gave me the suggestion, you can also say, I only want the states, or I only want the state of Utah, and then look for the county name that has UINTA in it. And turns out it does the exact same thing, right? Because the other county, the other Uinta County is in Wyoming. And so if you only look for the ones in Utah, then you're going to ignore automatically that one that's in Wyoming. Okay. For the sake of time, I'm going to move on to my next example. So what I'm going to do now is I'm going to try and visualize the cumulative number of cases in Salt Lake County. This is where myself and all of our volunteers are currently. So I'm going to use this table to array function. And I know, because I looked this up, what the county code is for Salt Lake County. And then I'm only going to look at the first year and some change of this data set. This is going to tell me the data for, let's say, the first wave of coronavirus, so pre-Delta. And then what I'm going to do is plot that data here. So run section. So this is the SLC COVID cases. This is the cumulative number of cases for this number of days. And you can see that you get this increase like this. But if you think about it a little bit, we've seen this kind of curve before. If I scroll up a little bit, this does seem to match this blue curve right here for infected people, right? So even though our SI model is pretty elementary, we might be able to actually use this model to predict the wave of coronavirus cases in Salt Lake County. All right. So let's actually try and do that. So what do we need in order to get these kinds of these two, the data and the model, to match? The first thing we need is the population of Salt Lake County, which I looked up a priori. So it's this population right here. And then I'm going to divide number of cases by the Salt Lake County population so that I have a fraction, just like we do in our model. All right. And then the next thing that we need is this infection rate. All right. This is that parameter A that I mentioned we can kind of manipulate based off of any data that we might have, based off of, let's say, the R naught of the virus or anything like that. You can do this really cool thing in these live editors, like create slider toggles for your variables. Just by coming up here to control, you can create a numeric slider so that you can like actually interact with your code. So I'm going to set A to be something like 0.083. And then all of this right here is basically the same as what I ran earlier in this hour. I'm going to compute the number of new infections, and then I'm going to update them over time. Okay, so let's run this. And now this last section, I'm plotting it. Oh, turns out I've already plotted it. So I'm going to run section. So this blue curve is the same thing that I showed you up here, except I've normalized it by the population. And this orange curve is the result of our new SI model. And yeah, the shape looks the same, but clearly we're not doing a good job of getting the number of people, right? So one thing we can do is we can decrease our value of A, and turns out, or a really nice feature of these live scripts is that as you change the toggle, you don't have to click run section. It just automatically reruns the section. And so you can see with this value of A, we are able to get a good read on the initial wave or the initial part of this rise in cases, but certainly around day 300, we're not doing too good, certainly because we're not getting this inflection to a lower or a flattening of our curve, right? So this is now where we get into, well, this is a reminder of the SI model. So all I'm doing is taking the number of infected people in each day, subtracting it from the susceptible people and adding it to the infected people. But based off of what we were doing with changing our parameters, we're now back here at our diagram for how to actually build a mathematical model. Right? We started with a real world problem, which is predicting the amount of cases from the coronavirus wave. We have kind of a more defined problem, which is the number of cases or the fraction of cases. We did make some assumptions earlier on, and I want to get back to that in a second. And defining variables, the number of susceptible people, the number of infected people, our total population, our infection rate. We built a model and we've gotten a solution. Now we're here at the analysis and model assessment, right? So clearly our model isn't doing too great at predicting the level of coronavirus cases. So let me ask you all in the little bit of time we have left, what ideas do you have for new assumptions or assumptions that we made that we need to change in order to try and get our model to look a little bit better? What do we know about the coronavirus that is not represented by a simple SI model? Mm-hmm. Yep. Those are some good ideas. Yep. Mhm. Awesome. Yeah. Yep, we got a lot of really good ideas over here. So we have, let's see, some people are talking about using an SIR model. So we add an extra group of people for people who have recovered from the virus, because plenty of people, they get infected, but then they get over the virus. And then for a while, they are no longer able to become infected, right? There's some literature out there that kind of suggests that you might be able to get reinfected with the virus, and then there might be things with variants and stuff, but we're not considering that right now. People changed their behaviors. We started wearing masks. We had lockdowns at the very beginning. That changes behavior, so you're less likely to be infected. That's certainly something you could try and take into account. Some simple stuff is stuff like death rate and birth rate, right? Our population is certainly not flat or is not constant over this amount of time. People have been dying because of COVID and because of other reasons as well. Another thing we have to maybe consider is the fact that we might not know if everybody gets infected, or we don't know whether or not somebody who got infected with the virus got tested and became a positive or a confirmed COVID case, right? So there are also that to consider. We certainly wouldn't be able to get our fraction of our population to 100% because we just wouldn't know if everybody got infected. The virus weakens and changes over time. Herd immunity might be something that you want to take into account. These are all really good assumptions. So going back to, let me make sure. Yep, people can get recovered and then reinfected. Yep, so you might have some kind of cyclical aspect to your model. And so this is kind of the process of mathematical modeling at work, right? Starting with real world problem and real world data, we're able to create an initial model. We analyzed it. We said, well, we need to tweak our model because right now we're not getting the results that we're looking for. We build the model again, get a new solution, and hopefully the next time our model looks better and better and better. With that, we are pretty much done with this hour. I just wanted to leave with some homework challenges. Try to compute for yourself the number of daily COVID cases, and also try to plot the 7-day rolling average of cases in a particular area. It doesn't have to be Salt Lake County. It can be, New York City. It could be your hometown, anything like that. But just try to play around with these table data structures and try and play around with some plotting functions so that you can maybe try and make some plots that you might have seen in the news or on websites and stuff like that.
Okay. Hello, everyone. So welcome back. So kind of as we've been doing with these sessions, right, in the second half, what we'll do is we'll actually look at previous problems that have appeared in the M3C or M3 challenge. And so this week, what we're going to do is we're going to look at the 2017 problem. And we're going to focus on the first part, right? Because M3 challenge problems come in 3 parts. But what we're going to do is we're going to focus on the first part, start talking about how we quantify the problem, initial ideas we have for answering the problem, et cetera. And then next week, I believe Keisha will start looking at some solutions and seeing a bit more in depth about kind of some of what's been submitted, both some of the winning solutions as well as some solutions that did well, but for whatever reason didn't make it to the top. Yeah, so this week we're going to talk about the problem, get some ideas together, get started on solutions. Next week we're going to analyze solutions. Okay, cool. So the problem and the data can be found here. And so what I'm going to do is actually take this and share it. Hopefully this goes through in the chat. Problem, data set, everyone. There we go. So feel free to go there directly. And so let's see. So let's go ahead and take a look at the problem, read through it, and then we're going to kind of start the discussion. So if you click the link, it'll take you to this page, 2017 from sea to shining sea, looking ahead with the National Park Service. National Park System of the US comprises 417 official units covering more than 84 million acres. The 100-year-old US National Park Service is a federal bureau within the Department of the Interior responsible for managing, protecting, and maintaining all units within the National Park System, including national parks, monuments, seashores, and other historical sites. Global change factors such as climate are likely to affect both park resources and visitor experience. And they give a reference for that claim. And as a result, the National Park Service's mission to, quote, preserve unimpaired the natural and cultural resources and values of the National Park System for the enjoyment, education, and inspiration of this and future generations. Your team can provide insight and help strategize with the National Park Service as it starts its second century of stewardship of our nation's park system. Okay. So from the general introduction, right, themes that we should expect: climate, possibly climate change, aspects of that, as well as looking at some national parks in particular. Okay, and so as I mentioned, right, M3 challenge problems come in 3 parts. Generally, the first part is set up in a way that most teams can get a solution that they can, justify and be happy with. And then part 2 and part 3, those start to differentiate kind of teams and solutions and really, highlight some of the exceptional approaches and write-ups, et cetera. And so to get started, what we're going to be doing is focusing, again, primarily on part 1. We'll talk briefly about part 2 and part 3 in a bit, but we're going to start with part 1. Okay. So what is part 1 of this question? Tides of change. Build a mathematical model to determine a sea level change risk rating of high, medium, or low for each of the 5 parks below for the next 10, 20, and 50 years. Okay, so the parks are Acadia National Park in Maine, Cape Hatteras National Seashore in North Carolina, Kenai Fjords National Park in Alaska, Olympic National Park in Washington, and then Padre Island National Seashore in Texas. You may use provided data on sea level to build a model. Explain your interpretation of high, medium, and low. Could your model realistically predict those levels for the next 100 years? Okay. So this is a question in a nutshell. We're asked to build some mathematical model to give a risk rating of high, medium, or low for the sea level change for these 5 parks. Okay. So, so then my first question is, what initial thoughts, questions, et cetera, do you have before starting on the modeling process, right? What are your initial thoughts or questions about everything that you've been told, and in particular, the parks to focus on? So take a few seconds, think about it. And actually, let me go back and I can keep the problem up here, but what are your initial thoughts about what this question is asking, what you might want to do, things like that? Just maybe take another minute, write down ideas. Well, so I have some kind of initial questions that I can share. And so some questions I had were, right, well, why were these parks chosen? Some of these parks I knew about, some of them I didn't. And so then the first thing I did after reading this was actually look into the parks and see, what there is about them. So one of the parks was Acadia National Park in Maine, right? And so right up here, looking at this picture that Wikipedia has provided, it looks like there are a lot of cliffs and rocks and things like that. And so already, especially thinking towards the question is asking about sea level change. And my question is, changing sea levels, is that going to be affecting this park substantially? Maybe in some parts. I don't know. Maybe that's a question to kind of consider going forward. Okay, so this is one of the parks. It's on the coast. Sure. Another park is Olympic National Park, which is Washington State, which is kind of on the other side of the country. Looking at this picture, a very flat beach, and then it looks like it has a hill that goes straight up. Okay. But even, right, kind of looking at this picture, it looks like Olympic National Park is primarily like a higher elevation area, say. So this is one of the other parks. There's Padre Island National Seashore. Okay, so southern Texas. It says it's on an island. Okay, so it's probably a lot flatter. So this is one of the other parks, Kenai Fjords. Okay, way up in Alaska. And looking at this picture, right, you can kind of see a glacier, a lot of mountains. So not a whole lot of beaches, at least kinds of beaches that you'd see in, say, Padre Island. But already what's interesting about Kenai Fjords is, right, there's, especially thinking about climate change and sea level change, right, maybe the glaciers are going to bring something interesting to this question. So there's another park, and then the final one, not far from where Keshav and I are from, is Cape Hatteras National Seashore. Okay, so it's on the Outer Banks, which kind of here's North Carolina, it's a little cut off. Here's Virginia up here, but it's very much on this kind of like stretch of land that juts out into the Atlantic Ocean. And it's not far from where I think Blackbeard was defeated, and that was near Ocracoke Island. But anyway, so Cape Hatteras, and then if you look at the map, right, kind of out here, so everything along the stretch is probably really flat, primarily beaches and coastal stuff. So that would be another consideration, especially right with sea level change, how that might affect things, etc. Okay. Right. So my question was, right, well, why these 5 specific parks? Common theme is certainly they're all coastal. Okay. But even among these 5 parks, right, there's a range of geographic features that we might expect would be important or play into kind of whatever solutions we come up with, right? Some of these are very flat and like very much on the coast. Some of these are more mountainous and higher up. But yeah, okay. So that was the first question, right? Well, why these parks? What's special about them? Some other questions that kind of came up, right? So in the problem statement, they said, hey, here's data you can use. Okay, so question is, well, what data did they give? And especially how is it relevant to these parks? And this third bit is kind of getting into kind of the problem development, which we'll talk about in a second. Right, but the question is, well, what kinds of risk might we be interested in, or might we want to start quantifying? Okay, and so certainly, right, with respect to sea level change and kind of beaches and low-lying lands, right? Are we going to lose land? How much land? Is that a concern? What's going to be the effect on kind of nature and the wildlife there? Maybe another aspect of risk would be, tourism and aspects in there. Okay, but we'll kind of revisit this in a bit. Okay, and so then, coming back to these questions, sure, we were provided data, so let's take a look at that data. So if you clicked on the data link, it's going to bring you to this page, problem and data for 2017 challenge. And if you scroll down, it was statement out the data. But if you look, there are a bunch of these links, okay? And so it's a lot of data. But if you read the bullet points, they specifically say, hey, this NPS underscore mean sea level, this spreadsheet contains data that might be used for question 1. Okay. And so then it tells a little about the data. You go on to the next one, NPS underscore heat underscore index says this spreadsheet contains data that might be used for question 2. So for right now, let's just focus on this mean sea level stuff. So if you click it, it'll download a spreadsheet. That spreadsheet is right here. Open it up. I'll have a few definitions. So first one, MSL trend. That's the mean sea level trend values, which are calculated using local mean sea level observations from long-term tide stations nearest the 5 National Park Service entities of interest. Okay. So my interpretation is, this variable here is telling us how this mean sea level is changing. Presumably they have ways to compute that from these stations right along the ocean, but this is going to be how the mean sea level is changing for each of these parts. And then they say each is based on a minimum of 30 years of data. Okay, so they're already doing some sort of normalization and processing of the data before they give it to us to work with. Okay, and then the other variable is this 20-year monthly MSL. So monthly mean sea level data from tide stations nearest the 5 National Park Service entities of interest. So it's probably the same stuff, just for a 20-year range. Okay, and so it looks like those definitions correspond to these tabs. So we look at another tab. This is the MSL trend. Looking at this data, it looks like Acadia National Park, they have some numbers, and then for the other ones, they have some numbers. Let's take a look. So MSL trend value, presumably this is going to be the change in sea level, millimeters per year, for each of these parks. And it looks like this is the kind of mean data for however long your observations are going, okay? And then it looks like they also provide kind of this upper 95% and this lower 95%. And so my initial guess would be that, so this is the average of all of their observations. The upper 95%, certainly some years, the sea level rose even more. And so this is giving you a sense of, on average, kind of that upper range of that MSL trend. On average, the high is about 2.4 per year. The lower is probably about 1.96 per year, okay? But on average, the sea level is rising about 2.178 millimeters per year near Acadia National Park. Okay. So that's how I'm reading kind of this data. And then they have similar stuff with Cape Hatteras, Kenai Fjords, Olympic National Park, and Padre Island. Okay, and so they also have this link right here that we'll visit in a second. Let's take a look at this other data that they've given us, and that's this 20-year monthly MSL. So if you click here, again, stations, IDs, and then the national parks. And then looking through the data, they have, okay, so years, so 97 is repeated a bunch, and then month. So this row is probably 1997, January, and then they're giving the measurements. Okay. And so looking at the measurements, it looks like near Acadia, so this is millimeters per year. So overall, it looks like the sea level is rising by a tiny bit, but still rising, decreased in this month, but otherwise that. And then the other thing that's going to jump out right away is, oh, well, there are missing values. So if we're going to try to use the data, maybe we're going to make an assumption or say something about how we're treating these missing values, okay, if we choose to use this data. But you can scroll down. It looks like around 2010. So this was for Padre Island. Looks like around 2010, they've stopped taking measurements for Padre Island. They go all the way down to December 2016. Okay. So that's the data that we've been provided. Okay, so then let's go back to this. So I guess quickly, are there any questions about the problem statement, the interpretation, some of the data that they've given us? So one other thing, very much inspired by kind of what Keshav showed us in the first hour, is, well, sure, we have all this data. Can we plot it? Can we get a rough sense of what's actually in this information? And so what I did is I copied all of this, at least this sheet, over to Google Sheets, okay? And already you can see a plot, okay? And so the statement that was made at the very start of the first hour was, well, Excel, Google Sheets, and any of these like quick spreadsheet software, they're really great for getting quick results and a quick sense of what's actually in, the data provided. And so kind of what I did here was say, so this is Seward, Alaska. Like I haven't played with the axes at all. All I've done is say, take the data for Seward, Alaska, and then produce a line plot from that. And so then, come on, this is what resulted. Okay, and so keep in mind that this is the monthly mean sea level. Okay, but in particular, this is a change recorded in that month. Okay, and so we see, some months there's like positive change, some months there's a negative change. Overall, it looks kind of, I don't know, doesn't look like a whole lot's changing. Maybe the trend is a little negative. But one observation, and let me refresh this so it cleans itself back up. One observation is, for Kenai, maybe not for Kenai. For Kenai, there are some missing values. But for a lot of these other ones, like Padre Island, measurements stop in 2010, but this plot doesn't really account for that. It just says, here's all the data you've given me, here's a visualization, okay? So I wouldn't include these as is in the write-up, but these are useful for getting a very quick sense of, what's in the data. And so looking at this, these are monthly changes. So at least until 2010, it probably looks like it's a net positive growth here. Similarly for Bar Harbor, which is Acadia, some positive, some negative here. By here, it's probably averaged out, some positive, and then over here, mostly positive. But anyways, okay, so this is just a very quick sense of what's in the data. Maybe it's starting to give you ideas of how you might want to use this and how you might want to, start getting at a notion of risk assessment for each of these parks and the changing sea level. And so with that, so let's start talking about the actual problem. Okay, so we look at the data, we have a sense of what these national parks are. And so, like last time, what we're going to do in the session is really talk about kind of building the model and getting started at some of these pieces, right? And so when you actually compete, of course, there's, once you have an initial model, start to look at it, get solutions and results, analyze what you have, and then go back and refine the process, okay? But here, what we're going to do is essentially the same activity that we had last time, where we're just going to start by defining the problem, making some initial assumptions, making some initial definitions for variables, and then see, how those play together. Of course, in your actual model, you might have to change some of the stuff, but here we're just making initial, steps for each of these red circles. And yeah, okay. So great, okay. Right, so the first step is, right, actually coming up with an initial problem definition, okay? And so this is where we say, great, we have this real world problem, right? We're meant to come up with a risk assessment in 10, 20, 50 years for each of these 5 parks, okay? And so this first step is saying, well, how are we going to quantify that stuff? And right, mathematically, what are the things that we're actually going to work with, okay? So take a minute or two, write down your ideas. They can be informed by the data. They don't necessarily have to be, but write down in chat your initial ideas. Yeah. So let's take another minute or two, right? So what mathematically, right, how might we start, how might you define risk in a quantifiable way so that we can see whether, or right, which parks are at risk? How are we going to start quantifying this stuff? Okay, so we have some suggestions. Oh. So let's see. So risk could be a number of building, trees, land area affected by water rise, certainly. And so one observation is, right, if you want to incorporate something like number of buildings, for example, that would be another data point or something to, try to find. Land area, certainly. A way to calculate one of the risks could be months when sea levels are higher than 1. Okay. So the mean sea level and that mean change could be greater than 1. We can correlate the amount of land that becomes covered by water to correlate that to risk and make risk levels based on the amount of terrain flooded by sea rise. Yeah, so a lot of these ideas here are around, how much land is lost. And so some of the ideas that kind of I came up with, certainly a similar one, right? How much land you lose, and which is certainly, one way to quantify risk. The question would be if we're able to find data and, have a method to actually compute this stuff, right? If it's easy to find data and if it's easy to work with it, great. Let's use it. Let's see which areas are risky. We might say that, well, like these lower lying areas might be riskier with respect to this definition of risk, but that's if we can actually compute it and get that data. Another aspect would be, right, well, what is the percent increase in the mean sea level? And so that's getting back to what was suggested, where, look for kind of months when sea levels are higher than 1, or maybe when the cumulative change in sea level is greater than 1. So I guess units would have to be incorporated here. But yeah, that would be another risk level or measure of risk, sure. Okay, so each of these, right, notions of risk come down to actually working with, right, that sea level height, say, and trying to incorporate it into some other data or some other aspects that we're able to work with. Okay, and so, right, so the other part is, well, what assumptions might we want to incorporate? And so, right, keep in mind that the main players for this problem are kind of land area, things like that, but mainly, right, sea level change, as well as aspects of, you might say, like climate change that are affecting that, okay? And so to kind of narrow our problem down to something quantifiable, maybe something that we can get data for, et cetera, what are some initial assumptions you might want to make about, right, the behavior of the world, behavior of the climate, and how sea level might be changing? So take a minute or so, think about it, type in chat, and then talk about it. So one assumption would be that climate change will increase at a constant rate. Sure. So my initial follow-up question would be, so when you say climate change, what aspect of climate change are you kind of talking about? But certainly whichever aspect you want to focus on, right? Sure, we can say it's increasing at a constant rate, or it's not doing anything wild. You could assume that the density of the water is constant with respect to temperature. Okay. So what temperature occupies different volumes depending on its temperature. So maybe hotter regions will have kind of water will take up, or same mass of water will take up more area. Colder regions, same mass will take up less area. So maybe that might be something that we want to account for and try to incorporate into our model. So another assumption, number of visitors will not change, right? So if we want to measure risk based on some aspect of tourism or the amount of people visiting or something like that, yeah, maybe this assumption will be, well, if there wasn't a change in sea level, right, we'd have kind of the same amount of people. And so then you're really getting at, right, what the effect of change in sea level is on how many people are actually able to visit and use and enjoy those areas. Yeah. So all great ideas. So some of the assumptions that I wrote down are the following. So, the data that we were given, we were told that, these are readings from certain tidal stations, I think they were called, and these were the monthly change in mean sea level. Okay, and so one question would be, right, well, especially for like North Carolina and Texas, if you have a hurricane or something that comes through, is that going to significantly displace water and affect the sea levels? I don't know. I don't do atmospheric science. And so maybe one assumption I'm going to make is that, well, I don't want to worry about that possibility and what kind of those sorts of weather events are going to have on sea level. And so maybe the justification is, this reported data is per month, right? So hurricanes, they exist on the order of like 2-ish weeks, a couple of weeks, just maybe about a month. They move around. I don't know. Questions that I'm starting to ask that I don't really want to deal with. So I'm just going to say, well, we're not going to worry about that stuff. Okay. Looking through the data, right, we saw that, well, there was a bunch of missing data. So the question is, how do we want to deal with that missing data, and do we want to incorporate it? And so maybe the way that we're going to incorporate it is say, well, right, if you have any block of missing data, take the data at one endpoint, data at the other endpoint, kind of interpolate the mean sea level change just by a straight line. It's probably not a very good assumption, but if we want to kind of dig in and work with all that data, and we want to interpolate, this would be a very kind of naive approach, but it would be an approach. It would fill in that space. Okay. And so kind of related to the climate change assumption about how climate change is behaving, question was, well, what's affecting kind of the change in the mean sea level? And so the assumption that I was making was that, well, right, and of course, this depends on the model that we set up, but maybe this change is primarily driven by two aspects, okay, over the course of however many years we want to work with. So maybe the first aspect is that, right, changing sea levels is going to be due to melting glaciers and ice sheets, okay? And so, if you have data about the change in maybe glacier volume or mass or whatever, maybe you'd refine the assumption and say, well, everything that is melted from the glacier goes into the sea. And so it's not trapped in any like freshwater lakes or things like that. Nope, it goes straight to the sea. And then the other kind of assumption is that, well, the change in sea level, the other way that we're going to say that kind of contributes to this change is the expansion of water due to heating. Okay, and so then we may be able to incorporate aspects about temperature and other quantities that are generally associated with climate change and global warming. Maybe the way that we can incorporate those is kind of through this assumption that yes, it will affect the sea level, and yeah. And so I can also say that, so some of these assumptions were inspired by even just Googling, right? Causes for changing sea level. Sea level rise is caused primarily by two factors relating to global warming. And so I guess here you can see why I decided to take those two assumptions. And looks like this comes from a NASA website. And so if you want to justify your assumptions, a quick and easy way to do that would be to, have this website as a reference for that assumption. And so then the other thing I Googled was kind of how the seawater, the temperature of the water changes per kind of, I guess, latitude and not longitude. and it took me to a Britannica website. And it says, where is it? Tropics, the ocean surface is warm year round, and it varies about 1 to 2 degrees Celsius or 1.8 to 3.6 degrees Fahrenheit. And so this is kind of the range that'll change, but it's roughly this temperature. 1.8 Fahrenheit seems cold, so maybe there's a typo here. Yes, anyways, my takeaway from this is, right, generally near the tropics, it's pretty constant. Mid latitudes, let's see, no, so this is the change. So mid latitudes, it looks like it can vary quite a bit. Temperature can vary quite a bit over the year. And then at the polar latitudes, so maybe near Kenai Fjord, it looks like it doesn't vary a whole lot, and it remains near kind of this constant 28 degrees Celsius Fahrenheit. And so maybe these are quantities and aspects that we will want to incorporate into our model if we so choose. Okay. Okay. And of course, depending on how you decide to set up your model and measure risk and things like that, you may want to incorporate some of these assumptions. You may not want to incorporate some of these. Generally, right, what you write down here is going to depend on what you write out for the other two pieces. Okay. Yeah, okay. So what else? So in the interest of time, skip ahead, but right, the other aspect of setting up your initial model is saying, well, right, what are the things that we want to actually quantify and kind of plug into some of these formulas, et cetera. Okay. So, think for yourselves, whatever model you have in your mind, what the important kind of quantities are. And so some that I came up with, certainly, right, the mean sea level for each park, right? Because, right, I mean, that's our target, right? We want to connect the mean sea level to some sort of risk assessment. Okay, so certainly we want to keep track and work with mean sea level. Depending on how we're quantifying risk, we might want to compute some sort of percentage increase or decrease. If we want to define risk as to like how much land is covered, we might want to actually have that as a variable. And so then this might take the form of some kind of like topographic map or something like that. That might be something we want to account for. And of course, depending on right, the model and the pieces that we want to incorporate, we might also want to explicitly keep track of the temperature near each park. Okay. And of course, again, all of this depends on whatever model you set up, right? It's your model. And so some of these may be necessary, some of these you won't need, but just some ideas. Okay. Right, and so one main takeaway is, right, whatever you come up with for each of these things, explicitly write out what they are. Sometimes, so at least in the examples that we've seen, right, problem statement has been clear. The assumptions are written out explicitly, oftentimes with justification. One big suggestion is whatever variables you decide to use and whatever quantities you want to use, make a table that says, here's the symbol, here's what it means. But be explicit about what each piece of your model is, and don't forget to write them up. Okay. Okay. So let's see. So, right, we've started defining our model. We've come up with the problem statement, written down some variables, come up with assumptions, etc. And so now now is when we would actually kind of, right, put together a model, compute something, and then say, hey, this thing we've computed, at least for this problem, here's how we're going to interpret it as either a low risk, a medium risk, or a high risk. And so maybe right now, as a question for you all, so I have some ideas on maybe some concepts that could play into whatever model you create. And so maybe my question for you right now is, right, how might each of these approaches, right, something statistical or something involving a differential equation or something involving some sort of probabilistic approach, think about it for a second, and maybe what ideas do you have for how, any of these three approaches might actually show up using some of the pieces that we put together, right, et cetera. So what might be ideas for how any of these three models are realized, or if you have another type of model, put it in chat. But take a second. What might these models look like for this problem? And then we can take a look at some examples. Right, so maybe it's a follow-up question, right? Building a statistical model. What data would we input to compute a statistical thing with? For a differential equation model, what quantity might we want to set up a differential or a difference equation for? So maybe take another minute. Okay, so one idea, so we can use statistical regression to extrapolate mean sea level over the next 100 years. Okay, so maybe, right, plug in your data for what the mean sea level is, maybe compute a line of best fit, and then say, okay, over the next 10, 20, 50 years, here's the value on this line of best fit. That's going to be, that's the model that we use to figure out kind of that mean sea level. That's one idea. Okay, well, so let's take a look at a few of these and kind of how some people went about using these models. So, and I guess before that, and these are all kind of repeated slides from last time, right? When you pick a model and decide to go through it, really use something that you're comfortable with and you have, some sort of familiarity, some sort of background in. Right, during the competition, you don't necessarily want to be struggling to learn something new and figure out how and why it works, and then implement it at the same time. If there's a simpler model or there's something that you're more familiar with, you can use directly. Okay. But anyways, okay. So one of these ideas was, well, let's use a statistical model. Let's try to extrapolate, from the data using, this mean sea level data that was provided, and then just see, what the trend is, and then see if we can compute something from there. Right. So for a few of these parks, right? Well, take, right, kind of the cumulative change in sea level. And then what this team did was, well, fit it with a quadratic curve. Okay. And so then this is the 2016 data. And so then if they wanted the sea level for, 2026, then they go 10 years in the future and it'd be somewhere up here. For Kenai Fjords, it looks like, right, using the same model, it's a downward trend, which all looks great. As soon as you get to Olympic National Park, data is a little more all over the place. Okay. And so luckily the team said, hey, here's, this R² value, which tells you a goodness of fit. Right, but this is what kind of the statistical model might look like, getting towards, right, extrapolating and kind of approximating or, trying to compute what the change in sea level is for each of these parks. Okay, so this was one approach. Another team said, hey, here's change in sea levels for Padre Island. It looks periodic. So let's try to fit it with some sort of sine curve. And so really what they did is they took an exponential and then a sine curve. Yeah, seems to work well enough. Say they use Mathematica, any code you want to use is fine. This was another approach. Let's see. And so one technique that a bunch of teams used was trying to come up with some sort of differential equation. Okay. And so we'll talk a little more about kind of possibly talk more about like what these pieces mean and what's in this model. But what they did is said, okay, well, what's the height of the sea level for a park at some time t? Well, you can get that by, they set it up via this integral, which if you're not familiar with, you don't need to worry about. They said, well, it depends on some parameters, alpha, beta, gamma, and it depends on kind of the temperature and how things are changing for each park. Okay? And so they were able to, get the data, they were able to solve some of these equations and then extrapolate the data and say, yeah, well, for this park, about 60 years in the future, its sea level is going to raise quite a bit. Okay, totally valid method, just another way of going about this. And so then the other thing I want to highlight is this probabilistic model that actually appeared in one of the winning submissions. Okay, and so kind of the details. So this was the winning submission. So if you're curious about what some of these symbols are and like what these pieces mean, their submission has more details. But what was interesting is how they approached it was they said, well, what is the probability that the sea level rise for each park is above some quantity? Okay. And in their write-up, they say, well, how we got these values of 300.8 and then like 91.4 and then below 91.4 is they said, well, according to, it was either NASA or NOAA, one of these government agencies, a sea level change of above 1 foot, which corresponds to about 300 millimeters, that's what these government agencies define as high risk or really bad. So they said, okay, well, based on this assessment, let's build this statistical kind of this probabilistic thing to say, what is the likelihood that each park in 10, 20, 50, or 100 years will see this much rise in sea level? Okay. And that was another approach, right, that teams took. And I think for this team as well, they didn't actually use that 20-year mean sea level data. They just used the kind of the yearly change and then that 95 upper bound, 95% lower bound kind of percentiles. So it was a different sort of way to start to get at some sort of risk rating based on change in sea level. Okay. Anyways, okay. Yeah, so this last probabilistic one explicitly had, a risk level. The statistical approach and the differential equation approach, as shown on the screen, didn't yet include some notion of, right, how are we going from the sea level change to some sort of risk score. Right, but keep in mind that whatever model you set up, whatever you compute, right, go back and answer the question that's asked, right? What is some sort of score for low, medium, or high risk of, where these parks are at? Right. Certainly, though, once you have a model, the question is, how good of a model is it? Okay. And so there are plenty of ways to start to get at that. Talk more about this in later sessions. As you saw, some of the teams had their R-squared values. So they're already kind of showing that explicitly, right? But things to think about. Okay. And so, sure. So parting ideas are going to be, well, great, you have an initial approach for part one. Maybe you start getting some results, et cetera, right? But for the M3 challenge, there are 3 parts to the question. Okay. And generally, teams that do well are able to make connections between all 3 parts. Okay? And so maybe the homework question is, right, for part 2 and part 3 of this question, right, what are they asking, as well as what are ways that you can incorporate your results from part 1 to each of these 2 parts? Okay. So in summary, so part 2 is saying, right, in addition to the phenomena listed above, National Park Service is investigating the effects of all climate-related events on coastal park units. Develop a mathematical model that is capable of assigning a single climate vulnerability score to any National Park Service coastal unit. Okay, so maybe in the results, right, for Kenai Fjord, sea level is decreasing. Okay, maybe that's good, maybe that's bad, we don't know. But right, if you come up with a score based on, right, amount of glacier and like ice sheet, etc., maybe Kenai Fjord isn't going to do very well. Right, so they're asking, well, right, come up with other climate related things that are going to affect the scores. And then finally, the last part is, right, incorporate visitor statistics and your vulnerability scores to create a new model that predicts long-term changes in visitors for each park. Right, so here for part 3, they're explicitly saying account for visitors. And that's also some of the data that they've provided. Okay. But anyway, so that's all the time that we have for. Hopefully this gives you a sense on, what's possible, and kind of how at least some of us start approaching some of these questions. What we're going to do next time is we're going to start with difference and differential equations. So that'll be the start of next time, after which we'll look at a few kind of submissions and do that analysis for the 2017 problem. And so with that, we're done. Thank you all for showing up, and we look forward to seeing you next week.